an associate professor in the Department of Electronic Science, University of Delhi, South Campus. His MSc in Electronics from Rani Durgavati Vishwavidyalaya, Jabalpur, and MTech from Delhi University, PhD from Delhi Technical University. He has worked in National Physical Laboratory. He contributed in developing new waveguide standards, enhancing the calibration range, successful international peer review, inter-comparisons, maintenance of quality control document, calibration activities, establishment of 13.56 megahertz based plasma enhanced chemical vapor deposition system, etc. He joined Department of Electronic Science, University of Delhi, South Campus as an assistant professor in 2013 and is now associate professor. He was involved in establishing new simulation and measurement facilities in department using signal sources, spectrum analyzer, VNA, and anechoic chamber for characterizing the microwave antennas and components. He has published more than 40 articles in international and national journals, and his works is presented in many international conferences. He authored a technical book titled Uncertainty Estimation in Complex S-Parameter Measurements by Lambert publication. He has completed 4 minor projects on microwave technology and guided many MSc and MTech students in their project work and supervising PhD scholars. He is member of various professional bodies, including IEEE Delhi chapter. His research interests include microwave component design and characterization, compact filter, planar antenna for mobile communications, MMO antennas, material characterization, and RF metrology. Sir, we would like to thank you very much for accepting our request and delivering this talk on a very important topic which is related with electrotechnical metrology. As measurement plays a very important part, certainly this particular topic will be very important for the industries, for the students and other participants. We have with us our Honorable Shri Badrinath Dikshit sir. Director sir, sir, would you like to speak 2 words, please?
Yes, Ashutosh ji.
Good morning, sir.
Good morning, and good morning to Patel Saab, other scientists, deputy directors, RSLs, and many other senior scientists, legal metrology officers of state government. So today is the very relevant topics. Earlier there was the most of the measurements were done in the mechanical systems, which was day by day converted into the electromechanical systems, and then later on it switched on the electronic modes also. But the artifact of the measurement itself is a solid systems, and it is designed. It is a designed way of length measurement, height measurement, volumetric measurement, or even for the weights also. The instrument for weighing the mass is also the electromechanical. Even though it is electronic, but you will find the design, you will find that a lot of the things are the electromechanical. So I hope that today's seminar will be one more steps ahead to know about the weighing and measurement systems, how to reach more through this very technology into the by way of the remote systems, even though the remotes are being used at the high precision levels in weighing and measuring instrument, in thermos, thermocouples, and even in the electronic balances, and in many other works where there is no need of any test measurement technology is required. So I hope that today's program will be very beneficial to us. I wish for the success of the program.
Thank you. Thank you very much, sir. Thank you very much. Sir, actually, we are also working on one very important project of dissemination of time through the servers for the telecommunication and all. So I think that this electrotechnical metrology will be very important. Now, sir, over to you. Professor Kamlesh, please, sir.
Okay, thank you. Thank you, Dr. Ashutosh Agarwal, for your brief for introducing me, and thank you very much for the organization of this national workshop on electrotechnical methodology for inviting me, and I hope uh, this talk will be beneficial for all the participants. Okay, good morning to all of you, and sir already mentioned that my today's topic is on the MIMO antennas and their characterizations for the 5G band applications. So you can see there are some new words most of you. MIMO, which stands for the multiple in and multiple out antenna. So this is the kind of antenna which consists more than two or three antennas, and most of these antennas which we are going to discuss is characterized for the 5G band applications. So today's topic will consist of mobile technology generations, 5G technology networks. uh, we'll have a brief introduction about the 5G frequency bands. What are the challenges we will facing or already they are establishing now in commercial aspects? What are the antenna requirements for the 5G so we can have the roadmap for the 6G application in future? What is the beauty or the features of the MIMO antennas? And one or two examples of the MIMO antenna we are going to discuss. And what are the different measurement techniques available to characterize the MIMO additional parameters in addition to the antenna parameters? And we will do some small analysis of the measurement results followed by the comparison. So mobile, everyone is nowadays having this mobile as one of the important tool they are using for multiple applications, starting from the mind-blowing performance to the reliable connectivity, broadband speed. So along with the mobile applications, you must observing that from the simple keypad, where we need to press the keys to operate the mobile, we are now using a display kind of a mobile pad to operate this kind of devices. Along with this simple device of mobile is consisting many kind of applications, like camera or any. Now they are having the um, GPS installed. So in addition to the simple listening and talking, we can have the multiple applications of this mobile communication, which is followed by the various generations. So the mobile, when it comes with the first generation, it was just starting, which consists of the analog device. Later on, in the 2G generation or the second generation, the digital voice and simple data can be communicated, where we can able to transmit some text or some messages. Followed by, we in the mobile 3G communications, there is an inclusion of the internet facilities, which is followed by the modulation technique wideband CDMA. And then in the 4G LTE, we are having the and more addition of sending the more amount of a data in terms of, like, say, high fan wide amount of the video files, etc. So along with the generations, or as per the data requirement, the mobile size as per the designs also get changes. Further, what is the depending on these number of applications, we need to have the device or the communication of the mobile signals to be very broad range, so which consists or which is defined in terms of a data capacity. So data capacity is given as a theoretically by Shannon, that the spectrum multiplied with the number of antennas and the log base to 1 plus SNR. So SNR stands for the signal to noise ratio. So when the signal is transmitting from one end to other end, from the transmitting antenna to the receiving antenna, the signal is facing the interference for the with the many signals available in the or having in the environment. So signal to noise ratio has to be maintained very high. This particular table is comparing the performance of various generation, first generation, second generation, three generation, fourth generation, fifth generation. Let's say we are talking about the fifth generation, which is now already established in many countries, including our India. where we are expecting the bandwidth is more than 100%, 1000%, and the operating frequency range be, let's say, 3 to 300 gigahertz. What is the what is the 5G technology vision, which is designed, or which is expected from the many researchers, that we are going to expect 1,000 times of mobile devices. So more number of devices require more number of data to be communicated at the same time. So we'll be expecting the mobile traffic just similar like we are facing the more number of vehicles. That means there is a possibility of traffic jam on the roads. So same is applicable with the signal propagation. So that's why we may face some kind of a drawback, or you can say the signal is being dropped at some time. So we certainly needs that the signal when transmitting from one mobile end to the other mobile end should be reached very fast. So that is governed, or that is controlled or defined by in terms of a latency. So if the latency is very small, that then we can say the data is running very fast. So latency, we are expecting that 1 second to 1 millisecond in 5G technology. And further, when we are talking about the use of energy for a very small duration, like 1 second to 1 millisecond, the expected energy which will be consumed by the mobile devices should be very small, from 400 nanojoules per bit to 400 picojoules per bit. So 5G network, what is the plan of the most of the commercial company to move from the 4G to the 5G network? They are planning to have the existing 4G technology or 4G base stations to convert into the 5G standalone base system by adding a small component utilizing the existing facility of the 4G only. So in the one second technique is that we can use the direct, we can develop the systems which can work in a 5G network or 5G new radio, and the connect, and they can be directly connecting with the 5G next generation devices, or those kind of a standalone mode system. Finally, we were going to shift to the 5G millimeter wave. So what are the different frequencies which are being covered in the 5G frequency band? 5G frequency bands are divided into two categories. The FR1 is consisting the 410 megahertz to 7.125 gigahertz, and FR2 band of the 5G is starting from 24.25 gigahertz to 40 gigahertz. So most of the communication application for general public is covering in the frequency range FR1, whereas FR2 is reserved for certain applications like the military and the health application, or you can say the medical applications for for the human health issues or health matter. So the 5G spectrum, which is now being announced in the India in the last year in August 2022, that is consisting about many bands starting from the 600 megahertz to 26 gigahertz band. There are various locations in our India itself that many companies, starting from Reliance Jio Infocom Limited and Bharti Airtel, Vodafone, and other groups, they are participated in many auction of this frequency band, and those have been allotted to the different uplink and the downlink frequency by the government. So what are the technological challenges which we are facing in the 5G? That the key technical issues consist of, when we're talking about the higher frequencies, in terms of the electrical, the frequency is related with the wavelength of a signal. So both are inversely proportional. So when we talk about lambda is equal to C divided by F, so if the frequency has been increased, the value of lambda or value of coverage by most of the system is reduced. So that is the main issue, that when we talk about the signal propagation in a very high frequency, like I mentioned in the previous slide, beyond 6 gigahertz, and their coverage is very small. So expectation is that we will place a more number of multiple repeaters in a very short distance, so the signal cannot be dropped away. And as soon as, when you also one more issue, that in most of the residential areas in current scenario, we are observing the high rise building. So high rise building is also one of the major issue which reduces the signal strength, and so the signal drop, or you can say the coverage is limited. So more number of signal repeater, or you can say the more number of mobile tower will be placed nearby, and so we can able to remove the coverage issue. Second is that we must also able to increase the uplink performance. That should be enhanced by addition of more number of electronic circuits and use of the simple or different kind of semiconductor materials. There are various industrial cases also. So the technical solutions for the spectrum use above 6 gigahertz to enable 5Gs are characterized like antennas should be smaller at higher frequencies, and higher frequencies require antennas with higher gain to maintain the link budget. So higher frequency automatically reduce the size of the antenna, and if the antenna size is reduced, we need to design the antennas in order to give very high value of a gain, as the value of the gain of antenna depends on the size of antenna. So proposes that instead of using a single antenna, we are going to use the more number of antennas at a single place, and those should be very massive, and they should able to provide very directional beam, as well as we can also use more number of phasor antennas. So phasor array antenna is a kind of antenna which is having the antennas placed in a series in a series connection or in a banner connections, and they can be excited in a different state or different signal of phase. We can also apply some beam forming technique. So by changing the beam forming, we can able to cover the more area in a very less span of a time. And like I mentioned, that we are going to use more number of mobile towers in a nearby region, so there will be the ultra dense small cell networks and so on. So we can implement the 5G network by along with a 5G along with the 4G network. We can also utilize the existing 4G core network for both the data and control planes in the non standalone mode. And also at the same time, we are expecting that, like we are having the 5G and 4G technologies, Wi-Fi signals will be also present in current scenario, which is like WLAN band or the Bluetooth band. Also, there is need to adopt the cloud-based radio access network for greater network flexibility and to save cost. So, why there is a need of the MIMO antenna, or what are the advantage we are going to have with the help of the MIMO antenna in the 4G and the 5G technology? Like I mentioned earlier, the channel capacity is defined as a bandwidth in bracket 1 plus m into n into SNR, where m and r are representing the number of transmitting antenna and the number of receiving antenna respectively. We can also define the signal to noise ratio in terms of the power signal, signal of the signal power, and the power available with the noise signal. So this is already given by the Shannon Hartlin very long ago. And when we talk about the frequency range of 4G and 5G, which consists of, let's say, for example, different band. For 4G, we are having the N1 band, which consists from 1920 to 2170 megahertz, which is having a bandwidth of 250 megahertz, whereas one of the band N78 in a 5G band is starting from 3300 to 3800 megahertz, consisting total 500 megahertz of band. So more number of antennas leads to more channel capacity, and so we will be able to achieve a higher data rate. So that is the idea, that if we are using more number of transmitting antenna as well as more number of receiving antenna, we can able to increase the channel capacity, and we can able to handle more number of data with the help of MIMO antenna transmission. So when we are talking about one more advantage of MIMO antenna, that if you are using the single antenna on transmitting end and the receiving end, depending on the availability of object, here you can think about object as a multi-rise building. And so by scattering from this multi-rise building, there is a possibility that the signal will reach from transmitting to receiving antenna in different path, and so the signal strength will reduce because of the destructive interference of this signal or at some of the locations or some of the point. So this is known as a multipath feeding, and we can use the MIMO antenna, like you can see in the second figure. If in the receiving end, if you use more than two antenna, at least one of the antenna will able to receive the good strength of a signal, and combination of the two antennas on the receiver side will able to give us high amount of a signal. So that is the one of the advantage of using the MIMO antenna on one side of the receiver. So the idea is that we are not going to use the line of sight communication in the practical wireless communication, and multipath feeding is one of the problem, which is due to which the receiver may get the different kind of a signal. And as we talk about receiver as a mobile and mobile phone, so mobile phone which is moving from one place to other place as with the person, so that may able to receive that may receive a different amount of a signal from the transmitter. So that is the problem with the multipath feeding. So evolution of the MIMO system, I will just skip this part very quickly. So the MIMO system is not coming in a single day. So there is a first we are having the single input, single output on receiver and the transmitter side. And in the second case, we can have that multiple antennas on the receiver side, which is known as a CMO, single input and single multiple output system. And followed by the next system is we can transmit with the help of multiple antennas on the transmitter side and receive all the signals on with the on receiver side with the help of single antenna. So that is covered with the MISO system. So combination of the CMO and MISO system is now giving us the MIMO system. So MIMO system is a kind of a system where the transmitter is consisting more than 2 or 3 antennas on one side and the receiver antenna on one side, receiver antennas on one side. So all these signals are being combined on the receiver side, and so the any signal which is reduced by the multiple feeding on after transmitting, we can able to compile all the data, and the signal strength will be higher or will be kept higher without any loss of the signal. So finally, we arrive to a simple formula of this C is equal to bandwidth in bracket 1 plus M into N into SNR. So if we increase the value of M or if we increase the value of N, we can able to finally increase the channel capacity. That means we can able to handle more number of data at the same time. So there are different arrangement how you can able to arrange or how you can able to connect the MIMO antenna in different for the different purposes. So these different purposes are also termed as a diversity scheme, that how the signals are being diverse while transmitting, and those will be captured from the receiver in different diversity scheme. So if we talk about different arrangement of the antennas location wise, that is consisting as a part of space diversity. And if we are able to change the radiation beam of the antennas, so that is termed as a pattern diversity. Population diversity is consisting one more part. I think many of the radical people will able to understand that we talk about the linear polarization and the circular polarization. So if the signal is sending in a linear polarization, the receivers should also able to receive the signal if the antennas on the receiver side are linearly polarized. If you're sending the signal in a circular polarization or transmitting the signal in a circular polarization, the antenna on the receiver side will able to receive the signal only if those are circularly polarized. So the signals polarization is covered with the polarization diversity. So MIMO can be implemented in 3 different forms. To explain more, these are the suitable figure where you can see the antennas are arranged like these two are arranged at a certain distance from each other on the transmitter side, whereas in this figure the antennas are arranged from each other at a certain distance on the receiver side. So those are those are defined by the position of the antennas. So that's why this is under the category of space diversity antenna. Okay, the pattern diversity, we are having the different pattern by exciting the antennas in a different order, which is having the maximum beam on this direction, whereas in other figure, the maximum directivity or maximum signal is transmitting on this direction if we change the pattern or the angle diversity. In case of the polarization diversity, we can have a signal which is propagating with a movement in the right hand side. We can also send a signal which can have a movement in a anti-clockwise direction where the signal can move from transmitter to the receiver side. We can also send the signal when the signal is linear polarized. So this is also termed as a vertical polarization. And whereas if the signal is sending in this order where the strength is on this direction, so this is termed as a vertical polarized. So depending on the requirement, we can choose one of the diversity. Okay, now coming to some real application or real design of the MIMO antenna for the 5G applications. So what is the approach for most of the researchers in the field of MIMO antenna design? They design the antenna based on the applications, frequency band, and what are the technologies used. Like most of the antennas in MIMO are using the planar technology, where they talk about the microstrip or the planar structures. We can also able to design the MIMO antennas in the stripline or other technology. And the after the design of the antenna, those should be validated with the help of 3D software, which is consisting of the computer simulation technology, one high frequency simulation software. This is advanced digital simulation, and so on. There are a number of applications. There are a number of softwares available. After the validation, one can fabricate the antennas with various technology. Finally, we are going to check the performance of the antennas with the help of various systems: vector network analyzer, spectrum analyzer, signal generator inside an anechoic chamber. And also we can see that our design is better, not better. We can apply a certain value, certain kind of a comparison with the previous designs. So as a brief introduction, what is microstrip antenna? Microstrip antenna is a structure which consists of a microstrip patch on the top of the substrate. This substrate is any dielectric material, and which is also supported by any ground plane. So this ground plane is normally made by the copper. The patch is also made by the copper. Okay, so you can see a real figure in this side where you can see only the top surface of the antenna. The bottom surface is consists of the ground plane as mentioned here. Okay, to increase the value of a gain, we can add more number of antennas. So this is one of the figure which is consisting more number of antenna. We are sending a signal from this. We can connect a signal generator on this on with the help of this connector, and we can apply or we can send the signal to 4 antennas. So this is simple structure. You can see how with the help of more number of antennas, more number of antennas, we can able to increase the value of gain. Okay, as a comparison, okay, these two antennas in figure B and figure C are designed at 2.2 gigahertz, and their expected gain is greater than 2 dB. Okay, when we compare the different parameters of the antennas compared to the single patch and array of 1 by 2. So this is the example of the 2 by 2 array. Okay, so this is the example of 2 by 2 array, and you can correlate their performance in this table. If we are having a comparison of a single patch with compared to the 1 by 2 array, the most advantage thing is the gain of the antennas. Okay, so the gain of the antennas and the angular width is also reduced. So the higher value of angular width is saying that the radiation beam from the antenna is larger. The radiation beam from this antenna is larger, whereas in case of okay, the antenna beam is very larger, whereas in case of the lower angular width, the beam is can be sent to very long distance with a reduced value of a width. So this is also termed as a radiation radiation pattern, and the width of this radiation pattern is known as a angular width. Okay, so these two are two advantages which can clearly seen on this comparison table, that if you increase more number of antennas on transmitter side or receiver side, you are actually getting the advantage of higher value for gain and the lower value of a angular beam. So this is a simple figure which is explaining the radiation beam of various antennas. So just to understand again, so this is the simple patch antenna model, and this patch antenna's 3D radiation beam, when the signal is transmitting out from the antenna, is look like this. So you can see the range is or the width is little broader. In this case, when we are using the multiple antennas in form of a array or in form of a more number of a MIMO antenna, the radiation beam is narrow. Okay, so this radiation beam is narrow. That means we can able to send the signal with a high strength to for a longer distance. That is the advantage. Okay, let's start with the design or discussion on the design of a MIMO antenna. Before designing a MIMO antenna, we first design a single element antenna. So these are made by the copper structure, and this is made by the copper structure. And like I mentioned, we are also having the ground plane. In ground plane, we made this kind of a slot. Okay, so this green color is representing absence of a copper, whereas this color is representing the copper. So copper or any conductor material. So this antenna is made in a two way. We can apply the input on this direction, or we can also apply the inputs from this direction. So this is a two-port antenna. That's why we can able to connect the two signals simultaneously or one by one. So this is, you can say, this is very simple antenna. It is vertical, it is horizontally placed, and this antenna which is horizontally placed. So combination of the vertical and horizontal place antenna can able to generate the circularly polarized antenna. So this is one of the, you can say, this is one of the polarization diversity antenna. Okay, before fabrication, we are going to simulate the structure. It is made on the FR4 substrate, which is having some properties like at the constant of 4.5, and the thickness of this FR substrate is 1.5 mm. The copper taken is 35 micrometer, and the CC software is used to simulate the structure. And after the simulation, we achieve the value of transmission coefficient as well as the reflection coefficient, which is also known as a scattering parameter, in a midway of 3.4 to 3.8 gigahertz. So in one of the slide I mentioned that the band we are starting for the 5G is from 3.3 gigahertz to 3.8 gigahertz. So this is what the antenna is made to work on, this particular band of N78. This is some physical dimension of the antenna, and this is a radiation pattern. Okay, so this is the radiation pattern of the antenna, which is known as a right now single element antenna. After simulation, we place the four antennas, the combination of the four antennas in this order, which is now consisting from port 1 to port 8. Total number of signals or total number of signals we can apply at a single time is the 8. So this is a combination of the polarization and space diversity scenario in the MIMO structure or MIMO antenna, and this is the design of a single fabricated model of the single element antenna for the MIMO antenna. And the figure 17 is representing the actual antenna with a various SMA connector placed on various on the locations. Okay, once we fabricate the antenna, we must able to measure the MIMO antenna characterization. Okay, so for the scattering parameter measurement setup, we have used a vector network analyzer, as you can see in this figure A, and we can also able to measure its radiation pattern with the help of this external signal generator and spectrum analyzer inside an anechoic chamber. So this figure is inside anechoic chamber. So when we talk about the measurement of antenna, we are talking about the introduction of metrology. So any antenna parameters which when we talk which can be measured should be compliance with the metrology aspect, that what is the parameter which we are measuring, and what is the measurement uncertainty associated with that parameter. So scattering parameter, like I mentioned here, we first characterize this for the scattering parameter. So scattering parameter is a is a transmission and reflection coefficient, which are also presented in form of the complex quantity like the x plus jy, and we represent the reflection parameters like S11 and S22, as you can see in this figure, and the transmission coefficient are represented by the S21 and S12. The measurement equipment which is available to measure this particular S parameter, is known as a vector network analyzer, and I'm skipping this a small part of the scattering parameter. So this is the vector network analyzer, which is directly give you the value of scattering parameter depending on the frequency range available with the network analyzer. So this is one of the model which we are available in which is available in our lab. It is JVH8, made is Rodent Swartz. There are number of VNA available, including the two port and the four-port network analyzer, and this is schematic of the VNA. We are not going to much in detail. So we have compare the simulated scattering parameter as well as the measured scattering parameter, and you can see this is the one of the performance of the simulated data of the S11 dB, which consists of S11, S33, S55, S77. So the signal which is being reflected from port number 1 and compared to the incident wave, okay, so this ratio is terming as S11. So like this is port 1, we are defining with the subscript 11, and the signal which is being sent input and reflecting from port number 2, we are taking as a S22. So depending on the port number, we are actually having the total 8 number of S11 parameter. So 1, 2, 3, 4, 5, 6, 7, 8. So we are having the total 8 number of S11 parameter, which is representing the reflection coefficient. If the signal is transmitting from port number 1 and we are measuring the power transmitting from port number 2, that is termed as a S21. Okay, so this is known as a transmission coefficient. So this transmission coefficient we are presenting here. So if we are feeding power at port number 1, measuring the power at port number 2, that is termed as a S21. If you are feeding the power at port number 1, measuring the power at port number 2, that will be termed as a S41. Okay, so signal is transmitting from port number 1 to port number 2, 4, 3, and other these ports are also termed as a transmission coefficient. So we compare this all transmissions coefficient in this figure, in this plot. At the same time, we also done the measurement of this scattering parameter, and we can easily see the comparison of the simulation data as well as the with the measurement data. So measurement data is not very much accurate as the simulation data, but we can see that the dip, like for example, in the red line in case of the S21, is almost observing in measurement data also. Okay, so in this way we can say our measurement of also compliance with the simulation data. So we have done the measurement of gain, measurement of the 3D 3 dB beam also. So to improve the isolation between the two elements, okay, so the our aim is that when we are sending the signal should radiate in the atmosphere, not jumping to or not transmitting to the other port of the or the other antenna element. So between these two we need to place a barrier electronically so that the signal cannot be transmit from port number 1 or 2 to port number 4 or 3. So in electronically we can place certain kind of a structure which should able to stop or reduce the amount of transmission between the two elements. So that's why we propose that we can use this kind of a structure, which is also known as a split ring resonator. And the next version is the complementary ring resonator between these two. And we observe that when we place the three structure between these two, we can able to reduce the amount of transmission from this port to this port. So we have placed this structure complementary split ring resonator, a set of three between these two rings, and so we can able to increase the value of isolation. Okay, so let's say this is the port number 1 and this is port number 3. So we check the performance or transmission coefficient between port number 1 and 3 by introduction of 1 and by introduction of a 2. We could able to reduce little amount of a transmission between the port number 1 and port number 3, while when we add the third splitting resonator in between these two, we can able to reduce the transmission between these by almost 17 dB. So we have finalized our design that we should incorporate a set of three splitting resonator to reduce the transmission between port number 1 and port number 3. So we compare all the scattering parameters simulated and the measured S11, which are almost same in the desired frequency band of 3.4 to 3.8 gigahertz. And then we also compare the performance of the MIMO antennas and the CSSR loaded MIMO antennas. Okay, you can see the structure here, MIMO antenna and the CSSR structure, where the value of S2, S31 is highly improved on placing the CSSR antennas, which is represented by the pink and the blue color. Okay, the pink and blue colors are having the low value of transmission between port number 3 and port number 1. So these all are the measured data. So metrology plays a role that how much accurately these measured data are correct. One can able to check with the estimating the uncertainty budget. For the antenna measurement, one can simply apply a simple measurement method, which is earlier available based on the modified Friis equation. We can able to obtain the value of a antenna gain by knowledge of the reflection coefficient, let's say at port of the second antenna or the receiver antenna, and the gain of reflection coefficient of the transmitting antenna, which is 1 here. Okay, we can also use the gamma L. What is the value of gamma L? That means the load reflection coefficient, and what is the value of the generator load reflection coefficient. So this is the formula available to obtain the value of G1 and G2, and you can see that one for the knowledge of G1 and G2 involve the measurement of this reflection coefficient 1, 2, 3, 4, and the value of R should be measured. That means the distance between these antennas should be measured properly. In addition with the what is the uncertainty component associated with the R. The next we are going to measure the value of power. Okay, so this receipt power over the transmitted power can also be termed as a S21. S21 is the ratio of the receipt power over the transmitting power. So either you measure the PR and PT and the assured uncertainty, or you can measure the value of S21 with the help of scattering, with the help of vector network analyzer, along with its uncertainty estimation, to check what is the value of a measured gain and the assured uncertainty assured with the gain values or the measured gain values. Antenna measurement is typically performed in an anechoic chamber, which is consisting of different shapes of the absorber. The role of the absorber is to absorb the any other path of the signal which is coming from the transmitter to the receiver. Okay, so you can see in this path the signal can reach directly from this is little bit this must be exchanged. The transmitting antenna is sending the power directly to the receiving antenna, as well as there is a possibility if antenna is little bit deviated from the 0-degree position, it may able to send maximum signal to the this side, and in absence of absorber some signal will reach to the this antenna. So the total signal which is received by the antenna is consisting of a two path as per this figure. So that is the role, that is the drawback with the multipath radiation. And to remove the multipath radiation, one has to make a chamber which consists of the absorber placed on their wall as well as on the ceiling. So the multiple reflections coming from the walls will be reduced or will almost zero while measurement performing inside anechoic chamber. So that is the beauty of the anechoic chamber. So this is the anechoic chamber which we are having in our lab, and in this lab is also equipped with a spectrum analyzer, which is model FSL6, and the signal generator DSG3060. So our measurement facility is up to 6 gigahertz. By having this kind of arrangement, we can able to measure the value of gain. Okay, and to compare a proper measurement, you need a standard of the gain parameter. So most of the metrology laboratories are using the standard horn antenna to perform the measurement and verification of the antenna under test. So by using this kind of anechoic chamber, we can able to obtain the radiation pattern, and this is the radiation pattern of the antenna design. The red is representing the simulated data, and the measured is representing the blue is representing the measured data. So there is a variations are observed between the simulated and the measured data of the MIMO antenna, which is done in the anechoic chamber. So this is due to the additional losses inside the cables or antenna connectors. We can also check the efficiency of MIMO antenna, although we have not done the measurement of radiation efficiency, which is defined as a power radiated over the power emitted by the antenna. And since there is a unavailability of the power measurement in the desired frequency band, and so we can check the performance of the MIMO antenna. This is simulation data only. So percentage efficiency in the band is about 80% to 75% in both the for both the antennas. This is the current distribution of the antenna, which is again the simulated results. So far, the measurement facilities are available to measure the gain of the antenna and the radiation pattern of the antennas. When we talk about the MIMO antenna, use of a MIMO antenna incorporates some more number of parameters, which is known as the annular correlation coefficient, total active reflection coefficient, mean effective gain, diversity gain, channel capacity losses. So this is the area which is not actually covered by most of the metrology labs, that when we talk about the design of a MIMO antenna and their application for the 5G and 5G communication, we must able to categorize the parameters of the MIMO antenna as mentioned here with the uncertainty measurement, or what is the uncertainty associated with these kind of a parameters. Number one. Number two, these parameters cannot be directly measured. So there are formulas available which represent that these MIMO antennas can be obtained from the measured scattering parameter. So the figure, so equation number 2 is representing the relationship between the measured scattering parameter and the value of the ECC. So we have done the measurement of a scattering parameter, and from there we have deduced these value from the measurement results, as well as we compare these parameter with the simulation. So this is the annular collision coefficient. We have developed the two antennas. One is a simple MIMO antenna, which is not consisting any CSSR. The second one we named as a CSSR loaded MIMO antennas. So this figure is representing the value of ECC from the simulation data, and this value is representing the measurement data. Okay, so here are the colors are representing the same value of ECC between the various port of the antenna. So here 1 2 is representing when the signal is transmitting, here how much the value of ECC measured at port 2 in terms of the scattering parameter. So this is the red color is representing this value, and so expected value is that the value of the ECC should be less than 0.04, which is preferred for most of the data, and this is the most of the data. That means if the value of ECC is less than 0.04 in the desired frequency band, the MIMO antenna is acceptable for the application. So this data are representing, or this all graphs are representing all of the MIMO antennas are having the ECC parameters less than 0.04. Okay, so that means our MIMO antenna is validated. Another parameter is the total active reflection coefficient, which gives you the idea that when we are sending the power at one of the port, how much reflections we are facing. Okay, so this is also possible. The reflection is coming from this port only, or the reflection is also coming from this port only. And if very small signal is coming, they can also able to send this reflected signal on the port number 7, for example. And as well as this can also be able to send some amount of a signal which is reflected from port number 5, and so is applicable port number 4 and 3. Theoretically, we understand since the port number 1 and port number 1, 2 and 4, 3 are away from port number 7, there is very less chance that the power may be reflected from this port towards port number 7. Still, there is a combined formula available which represent the role of all the active scattering parameters. So with the help of scattering parameter measurement, which is now using the complex parameter, we can able to calculate the value of torque, the total active reflection coefficient. The simulation data is using the equation number 3 to give the torque. So we compare the value of a torque which is obtained from the simulation and which is obtained from the measurement data. This is obtained from the measurement data. So these data are almost matching to each other. So that means our measurement is validated with the simulation data. Next is the parameter mean effective gain. So when we excite one antenna or when we excite more number of antennas, how much total gain we have obtained. So in this case, when we talk about the measurement of a gain, we are using only one antenna to be transmitted, like the student horn antenna, and our MIMO antenna is placed on a antenna under test. At that time, we can able to measure power from on received by the one antenna only at this location. So this does not giving us idea if we apply or if we are able to receive the signal from more number of antennas. So when we talk about more number of antennas which are able to receive the signal in a MIMO antenna, so that is giving the idea of the instead of using a single gain antenna, we must use another parameter that is termed as a mean effective gain. So it receives the ability of the MIMO antenna in a multipath environment, which is also defined in terms of the scattering parameter in equation number 5. So as I mentioned earlier, we have measured the value of a scattering parameter with the vector network analyzer. We can able to calculate the measured value of MEG from the measured scattering parameter. Further, we have compared the value of simulated MEG with the measured MEG, and you can see all the performance is almost same, and same is applicable for other port MEG parameter. The one of the more important parameter is diversity parameter, that is shows the enhancement of the overall system performance compared to a single element. So single element, as I mentioned earlier, is consisting only the one antenna, whereas the MIMO antennas compare the value, whereas the MIMO antenna compare the all gain of all the four element. This is one, like this is two, this is three, and this is four. So we are going to check when we use the gain of the single antenna or when we use the gain of the MIMO antennas, how the MIMO antenna should able to give the gain at least 10 dB higher than the value of a single gain. So the formula is derived from the ECC for the DG, and once we are having the measured value of S parameter, we can calculate the value of ECC, and from there we can able to observe the measured value of DG in terms of the scattering parameter. So this is a figure which is representing the value of MIMO from the measured value of DG, dB, and this is representing the value of DG for the CSSR loaded MIMO antenna. Okay, which is almost equal to, in for most of the frequency range, our frequency range of operation is 3.3 to 3.8 gigahertz. In this particular band, we are having the value almost equal to 10 dB. So that also fulfill the property of the MIMO antenna. The last parameter is the channel capacity loss. That means when we are sending the various signal from the MIMO antennas, how much signal will be reduced in terms of dB power or in terms of dB value when the MIMO antenna is used in any system. So this MIMO antenna we have designed for 4 port, and to define the loss, the parameter channel capacity loss is used. Okay, so this is the formula for the channel capacity loss, and you can see the equation 9 and equation 10 is also representing the value of the part of this matrix, which is the antenna correlation matrix, is obtained from the measured value of scattering parameter. So from the measured scattering parameter, we have deduced the value of sigma ii and sigma ij placed in this formula, equation number 8, and this formula is further placed in equation 7 to obtain the value of a CCL. So this small set of equations are correlating that once you are having the scattering parameter with the uncertainty component, we can able to calculate the value of CCL with the uncertainty estimation. Okay, so this graph are representing the value of SCCL obtained from the simulation, and this is representing for various number of a port. Okay, so like this is consisting the 2 port, and this is talking about the value of CCL for the 4 port MIMO antenna. We have designed the 8 port MIMO antenna. So one by one, we have checked the performance of MIMO antenna. This is 8. So all the values are less than 0.5 bits hertz, bits per hertz bits per second per hertz, and so the signal will be the CCL is very small, less than 0.05. So we can use the most of the antennas which are represented by these colors for the MIMO application in 5G. Finally, on comparison with the presented MIMO antenna with various reports earlier in the almost same frequency band, we have checked our ECC. Okay, so like we can say, when we talk about comparison with this 19 and this paper, which is having the number of ports 8 and 8, and finally we can also compare with this one. So in the same band, we are able to have the ECC, which is maximum 0.05. They are presenting 0.0002. We are able to have the torque value better than minus 17 dB, and the CCL is 0.4. So most of the previous reports does not talk about the CCL, and we have presented our work in terms of a CCL. So conclusion is that as for this presentation, the MIMO antennas are extensively used for the 5G application and now for the future 6G applications. And along with the simple antenna parameters like the gain and radiation pattern, there are new set of the parameters which are defined for the MIMO antennas like the ECC, torque value, DG, MEG, CCL, etc. So our future antenna metrology for the 5G and 4G applications should able to derive in order to develop the measurement system as well as the calibration techniques to calibrate all the MIMO antennas, for the MIMO parameters. Number one, as you can see that since the channel capacity depends on the number of antennas, in future the MIMO antennas will consist of more number of antennas. So their size will be little bigger even we talk about the higher frequency applications. So the antenna metrology not only require theoretical background since we are going to incorporate more number of antennas on the receiver side as well as on the transmitter side, as well as they also require sophisticated equipment which are able to provide the necessary accuracy and purity of the measured data, especially for the new set of the MIMO parameters. They are way ahead to do the research as well as to develop the measurement and calibration techniques in various applications consisting of the near field scanning techniques, antenna system ranging from the military radar to the interplanetary spacecraft. Since we are planning to use the FR2 band for the military applications starting from the 24 gigahertz to higher frequencies, till we are waiting for the 6G band which are having the frequency range from the 60 gigahertz and so on. We are we also need the advanced antenna system which can able to operate in the motion as well as frequency range from 1 gigahertz to 1 terahertz 10 to power 13 gigahertz. And there is a requirement of development of polyplanar near field measurement. And when we talk about the small size of antenna measurement, and we wanted to reduce the overall anechoic chamber, one can look for the compact antenna test range for the 5G near radio open test over the air massive MIMO antenna multi-user test applications. Last, the far field multi-probe anechoic chambers for the 5G the NR and OTA testing of the massive MIMO system. So these are the techniques which are developed in most of the calibration laboratories for the radar as well as the antenna applications. Along with this, I end my talk here, and thank you very much for listening.
Thank you very much, sir. Thank you for your brief presentation. Certainly, it is a very good exercise, and we will learn, our people will learn a lot from this. Sir, I would like to request you to kindly share your presentation with me so that we can share this with all the participants. And this video which we have prepared this time, we will also share this video through the through our YouTube channel and all, if you kindly agree.
Sure. I will share my slide.
Thank you very much, sir. Thank you. Thank you. I think with this, I would like to thank the participants, the expert, Dishusab, my NIC team from the department, and all the participants. Thank you very much for joining us. Next week, we'll meet again with the next topic.
Okay. Thank you.
Sir.
Thank you very much.
Thank you, sir. Thank you. Oh, we have not taken the photographs. I'm sorry. I would like to request all the participants to kindly switch off your mic and switch on your video. I'm sorry. I forgot to take the photographs. Please. Just a moment.
कहाँ दिया रे बाबा चलेंगे कहाँ वीडियो कहाँ दिए
Kindly switch off your mic, please. Anybody who wish to speak anything?
सर प्रेजेंटेशन जो है
क्या
अनशेयर
बोल रहे
कर दीजिए, वो फोटो नहीं निकले।
VGS वाला मैं बोल रहा हूँ, इस वक्त खत्म हो गया है,
When
वो
you share the presentation.
माइनस में जा रहा है, जब देखते टोटल करके
Kindly switch off your mic. We are able to please. Kindly switch off your mic.
स्क्रीनशॉट भेजे हैं लोग।
Sir, kindly unshare your presentation. Thank you. Thank you. Thank you very much. I will share this presentation shortly in the groups, as well as this video will also be available on our YouTube channel. Thank you.
Thank
Thank
you,
you very
sir.
much. Thank you all. Thank you.
Thank you all.